Yeah, so this session will be like 20 minutes of combinatorial game theory, and then 20 minutes of different spectral classes of stars. So I am Parth Sarda. I am at IISER Pune, which is like a research institute in the country of India. It's situated in the city of Pune. I'm a third year BSMS student here. And so for the last 2 summers, I've been working on combinatorial game theory, which encompasses a lot of different games that you might have been seeing, like which are played a lot of times. So like you might be knowing about chess, you might be knowing about games like Go. All those games come under the broad view of combinatorial game theory. So in this talk, I'll be actually like taking you on a journey about like different kinds of combinatorial games. I'll be introducing stuff like XOR addition, and then which is similar to a binary sum. So you convert, for example, a decimal system number to a binary number, and then you actually do a sum of that, which is very useful for a game called NIM, which is like the basic combinatorial game, which the whole of this field is built around. So as you can see, I'll be introducing concepts like and then combining logic. I'll also exploring stellar sciences. And also, one more question. Can you see some part of this meeting on the screen such that I'll minimize it or something if it's becoming a problem?
We just see the slide that you're sharing.
Oh yeah, sure. Okay, then that's cool. So yeah, as I said, the part one will be about combinatorial game theory. So basically, combinatorial game theory is any game which has perfect information. It works on the principle of combinatorics, which are very easy, and actually kids who actually are in middle school and high school can easily learn about those concepts because they are not that uh, like information heavy, or you might not require any prerequisites, which a lot of different areas of mathematics requires if you want to go deeper into them. And essentially part two would be about B stars, as well as like I'll also be doing hands-on session on Stellarium, which is a very cool software in which you can actually like uh, explore a lot of stars, stellar clusters, also actually predict eclipses, also have views of eclipses, a lot of cool things that you can do using that software. Uh, so yeah, let's begin with the part one of the talk. I also have some websites where we can play some games because I don't want the talk to be very information driven, and like because again this is more about how learning is done. And what I felt my classes and school lacked was like going beyond a certain level of teaching. So like actually implementing those examples, doing applicator stuff, those are very key components of learning. And a lot of people, if when they want to actually like if they're asked what would they prefer, the way they want to be learned about certain concepts, they would prefer this way rather than the other ways. So yeah, this field actually is a very novel field. This came in like in the last 100 years. Again, this was developed by the great minds of John Hurton Conway. Some of you guys might know him from the famous Game of Life. He contributed also in number theory, where, like he found certain kinds, uh, uh, I think Conway sequences, and then also he also came up with this crazy knot problem called the Conway knot. So, like basically simplifying a Conway knot into a certain order of knot was like an unsolvable problem. up until 2021 when a young New Zealand mathematician solved it. And so, as I was talking about, these are like perfect information games, uh, which basically means they don't need any kind of, they don't have any possibility or probability with them. So, if those games are all about all the different combinations, for example, if you play tic-tac-toe, uh, it's all about, for example, I play in the center, you can play anywhere, but at this point, the probability does not really matter because it is all about combinatorics. You can actually, if you have enough computational power, you can calculate all the different sequences and actually find the most optimal move for that given point. And so generally this is true, but you also have some kind of loopy games, which I was working in this summer, which are very interesting. You have like a certain stopper theory which comes in hand. So like that is again, this stopper theory was developed in the last 20 years. So very novel. Also, like it is developing a lot. Like there are people who are actually coming up with new rule sets within the stopper theory. Also, like like the normal basic combinatorial game theory is like, so. For example, you have things like atomic weights, which are a part of combinatorial game theory. They are being implemented in stopper theory recently, and then we have basically the basic game elements of a combinatorial game. They include a set of moves. So objective, essentially, as you guys might all know, is to win the game. But I mean, if you want to actually go do a deep dive about them, it can be also to actually think which player will be losing. So in combinatorial game theory, you have two kind of major rule sets, which I think will be written, I think, somewhere ahead. One is normal play, which involves whoever plays the last move wins the game. And then there is misère play, which is about whoever plays the last move loses the game. So they are completely different rule sets on their own. And what is interesting is some of the games have been solved for normal play, but they have not been solved for misère play. So it's quite interesting looking at those misère play games. Uh, Rather than actually dwelling too much on this, because again, this is very theoretical part. Yeah, again, tic-tac-toe, Go, Connect Four, Gomaku, Domineering, checkers, chess, uh, Amazons. If you have heard of that game, then there is a game called Toads and Frogs. All these games are combinatorial games. You don't require any kind of luck-based system or any kind of probability in these to win. So this game, which is given here, is something called Toads and sorry, it's called Fox and Geese. So a cool part of this game is it can become loopy. So it is like you start with a certain condition. So you have four geeses. Wait, if I think it'll be difficult to make it here, but I can try to make it. So yeah, so for example, you have like a small board. I mean, I'm making it very smaller. I mean, this is not how it's played essentially, but yeah, it's played on an 8 by 8 board. I'm simplifying. So essentially, you have, for example, a fox here. I call it F. I'm denoting it like this. And then you have something like a geese. So your main agenda is to prevent fox from moving, which can be done by moving here. Again, the moves of, for example, geese are diagonal, so it can move diagonally southwards anywhere, while fox can go diagonally northwards. Uh, but sorry, I forgot to add one thing. Fox can also go diagonally southward as well as northwards, uh, and geese can only go southward. So geese have a finite number of moves, while fox cannot. So, for example, if fox get to play first, all he can do is basically play here. Then geese is basically caught, and then he loses the game. But fox now has an unlimited number of moves because it can keep playing, but geese will have to go down and then stall at the end of the day because she cannot actually go up. And so it will be an easy win for Fox. And you define these games by something called the G. Sorry. And G is basically the game value of the game. So this is basically based on the outcome. For example, if G gets to play first, all it can do is basically go here and the game ends. So for example, geese being so in combinator game theory, you actually use left and right players as the notation. So basically, left and right are like the two players. That's like the convention that is being used. So also some people use blue and red, but I mean, yeah, left and right are also like the most popular one. So for example, GL, this is the left player. So it can just go here and then it wins. So, but Geese does not have any other move. So at this point, this can be called as a null position. So, and then this is basically on. So basically, because the way Fox goes here, it can have an infinite number of moves. On basically refers to an infinite number of moves. I mean, it'll be a bit difficult to explain what on is because again, I am limited for time, but you can think of it as like if you are on a board in a chessboard, for example, with a rook, for example, you can basically keep on moving because rook is the only piece available in the chessboard, and it can basically go on forever. It has infinite number of moves. It is even like so basically on actually like if you actually look at it in terms of a number theory perspective, you can because on cannot be bounded as such. On can be said as greater than the total number of natural numbers that exist. I mean, again, this is a bit high level stuff. I mean, I would not like to go deeper into it, but so basically, Conway did some research on this, and uh, so you because you for example, for natural numbers, you can only have and for example, they go from so they are from 1 to n, and I mean that n can, for example, can go to infinity. But if there is one way of actually isomorphically mapping them, and if you map them essentially, it turns out uh, the number of moves that a player in on has is more than the number. So basically, you won't be finding one-to-one mapping or an isomorphic mapping if you do the mapping here. Yeah, if you guys have any questions or anything with regards to what I'm saying, please interrupt me. This is supposed to be a very open talk. Like you can ask Vishay, you can actually stop me anytime. I'll happily answer your question. So yeah, let's start with our game, which is the game of NIM. And how you play this game is pretty simple. You have a certain number of heaps, and you take out a certain number of coins from that heap. And the person again who plays the last move wins. This is an example of a impartial game, which basically refers to the fact that this game can only be determined by the position, like the placement of pieces or like whatever doesn't matter because like the player choosing the same coins, you don't have any distinction between the pieces or anything. So yeah, and then the cool part about this game is it is very simple to solve. I mean, there was this guy called Boughton who in the 1960s solved this game. I mean, found the winning strategy, like found actually classified every single position into a set of N and P positions. So N is basically the first player winning positions, and P are basically the second player winning positions. And the solution is pretty simple. And it's also very elegant. So, for example, let's play a game. For example, I have. So, did you guys get to know about the rule set? So, the rule set is you can take out any number of coins from a single heap. Uh, Obviously, they cannot be more than the heap size. For example, if you have like, let's say, 5 coins in heap one, you can take out uh, 1, 2, 3, 4, 5 coins from that heap. But you cannot actually like take out a certain number of coins from one heap and another set of numbers of coins from the other heap. You can like only select coins from one singular heap. And basically you have alternating play. So like if you play first, I will play after that. If any one of you guys would like to volunteer, it'll be amazing to actually play a game of NIM with me. If nobody's interested, I can actually continue with the game. But yeah, it would be nice if somebody volunteers to actually play a game. So 5 and 3 coins in a heap. And so for in a set of two heaps, what is really interesting is you can actually like make them equal. So for example, I can take out 2 coins from here, it becomes 3 and 3. And now I can just copy whatever this like the second player plays. For example, he takes out 2 coins, I take out 2 coins, and then like he again the another like the only option left for him is like take out 1 coin. So you can simplify this by yeah. So again, through NIM, I'll be teaching people about binary numbers, which are very important when it comes to computation. So like essentially all the computation that you do comes in form of algorithms which will basically work on bits, and bits basically occur in two states. So you have a one and a zero state, and so every single calculation is converted into the binary language, and the given operation is performed in that language, and the output basically based on what you get by the operation is translated back. And okay, probability and statistics is not really used a lot when it comes to combinatorial game theory. they're used normally in game theory. So if you might have heard of the prisoner's dilemma problem, it is like a game theory problem because you have you have a certain payoff matrix. So the problem is like about, uh, for example, you have two prisoners and they can either confess to the crime that they have done or they can like not confess and essentially like so they have a you based on what like what they do, what action they choose, they have like binary action at this point, either confess or not confess. You have a payoff matrix and you try to maximize that payoff matrix in order to find the most desirable outcome. So it's also a bit of psychological thing because again you also have a probability assigned to that. So you also have probability matrices uh, which are like which actually are multiplicatively adding. So for example, you have a set of 4 or 5 uh, these prisoner dilemmas problem going on and on, then well, you can actually do something like for p raised to the power 5 into the given payoff matrix that you have. That will be the desired payoff that you'll be getting, or like the result that you'll be getting at the end of the prisoner dilemma problem. Again, these game theorems also teaches you about proofs because again, they're easier to prove in comparison to like, for example, number theory problems or topological problems and like any difficult problem in mathematics. They teach students about proofs very easy. Like everybody likes games and but like, you can. I mean, I'm actually going deeper into games, but you can just play games and understand what is happening. Like for example, if you play name, you'll actually understand like a lot of cool things why that happens and like you can try and work them out. I mean, you'll be learning a lot of mathematics through that game. So yeah, that is also fun. Graph. So yeah, I mean this is like introduction. So as I said, I mean partial games. Partisan games are like you have a board position. For example, chess is a partisan game because both of them have different board positions. I mean, it's not like the board is not similar between them. So like the game board, if it's distinct, then it becomes a partisan game because you have like different game positions. You can have like those tiny differences. And they also have the different outcome classes. So you have, for example, people winning regardless of who is playing first and second, which are basically which are defined as L and R. L is basically the left player winning, regardless of whoever is starting the game, and R is basically the right player winning, regardless of whoever is starting the game. So these kind of things all come in a partisan game. They have like their own outcome classes. And in loopy games, you have like a set of 9 outcome classes. It's really interesting because you also have like the stopper theory applying, which actually like reduces everything. You have how can you prevent loops and stuff like that. Active research problem. So, yeah, impartial games are very simple games. I mean, personally, people call them boring games. I also find them very boring because they're solved at this point. They're not very interesting. If you actually computationally check their complexity, they are not like, for example, a lot of particle games are piece-based complete, which means like the amount of algorithm that you need to do to find the optimal winning strategy for a given game board is bounded, but it's a very large number. Like so it is not like you don't have a piece space time assorted to that. And the same thing with us. Uh, for impartial games, you don't have that. I mean, basically, those games are like literally solved. So for example, you look at a given simpler sequence. Uh, for example, a sequence which actually is regular and is cyclic can be thought of as impartial games because you have patterns and using those patterns you can find out the result. While for partisan game, it's not that easy. I mean, you need to solve those algorithms which which can get really tiring depending on like the how big the game board is you're talking. Again, as I talked about, P position is like previous player winning or the second player winning, and N position is like first player. And yeah, the rules of NIM, as I already told, you have a heap, you have certain number of heaps. Uh, two player take in turns, alternating play, and then as I started with a classic example, 3-5 stones. Basically, if I'm the first player, I'll make them equal to actually like then I can just copy. You can apply the copy strategy. But the problem is if it's like something like n and n, so you have a certain number of heaps in the first stack and like the same number of heaps in the second stack, then I'm lost. And if the player plays optimally, if he like messes up somewhere, then I have a chance of winning because he can again apply the copy strategy that I talked about earlier. Yeah, you do this XOR sum, which is so you can convert every single number into a binary code. For example, 3, as it is written here, can be converted into 011. It comes from the fact that if you have, because again, binary numbers cannot be greater than 2. That's the whole concept. So, for example, decimal system that we apply, our numbers don't go like over 10. So, like it can be thought of as like 10 is basically like if you actually give 10 as the value of alpha, 10 is equal to 1, 0 because you have 1 in the finals place. So the same thing with if, for example, a torsion system, for example, then they would be going more than 3. So again, 3 would be written as 1, 0 there in a tertiary system. In binary, uh, 2 is written as 1, 0, so 3 is 1, 1. So 4 will be written as 1, 0, 0, 2 raised to the power 2, again, because 2 is 1, 0, you just add 1 here, becomes 1, 0, 0. 2 zeros on the right side, signifying the power 2. 5, for example, you just add 1 here to the most distant left place because 6, for example, would be 1, 1, 0 because if you add 1 to 1 in the most distant right space or like the units place, for example, uh, that's what it's called in the decimal system. You just add 1 and 1, it becomes the 1 gets carried over, this becomes 0 because again 2 is 0 in the binary system, and then you get this. So for example, if you're doing a sum, a binary sum or XOR sum, as it's so rightly called, I mean in game theory language it's called nim sum, but again that's what game theory is called. So you do this sum, you get well, one it becomes 0, this one and this one combined to basically give 1, but because this is already 1, you already have 1 in here. So it's like you're doing carry over here. Wait. You're doing carry over here. So it becomes 2 again. That becomes 1 here. So 1 is again getting carried over. So at this point, you get a new. But the elegant thing about nim sum is you the carryover, final carryover is not counted. So at this point, if you do the sum of this, it would basically become more like 0. You don't do the carryover because it's a name sum or the XOR sum. Binary sum, you would do a carryover because that's how things work. And so this becomes uh, 0, 1, 1. So it's 1, 1, 0, which is 6 in the decimal system. So their name sum is equal to 6. So if I mean, you can represent them by something called the 6 star in like combinatorial game theory. And again, so how can we actually solve this? Because we know 1, 0, 1 gives us uh, a nim sum of, sorry, 101. Uh, so we can actually just convert this to 011 because this will give us the nim sum 0. We need to make the nim sum 0 in order to uh, be winning, because again, the winning strategy in nim is to actually get to nim sum 0. So if I convert this 101, which is 5, to 011, which is 3, I would get nim sum 0. And my whole point for winning is to make nim sum 0. So I'll do that. I'll take out the 2 coins or tokens from the second heap, which has 5 coins or tokens. And then basically, whatever that other person, I can just copy at this point. Because again, if you have the symmetric set of uh, stuff, like a symmetric set of numbers, their nim sum would be 0 at this point because they would have the same pattern. For example, it will be something like x when x is equal to 0 and 1, and the same thing will be x is equal to y because they are the same at this point because you're copying at this point. Uh, I already talked about this. So you make the heaps equal in a two heap case, and in unequal heap case, what you can do is you can basically take uh, basically make them equal. But in equal case, you cannot do anything as the first player because like the second player will be copying whatever you do. So yeah, this is like a binary addition. This is how you call it. Not binary XOR addition. We did this again. Simpler thing. 1 1 becomes 0. Sorry, my bad. It's here. So it's 1 0 is 1. 1 1 is 0. So you have 1 1 0, which is 6. And we can simplify this easily. You can actually do it for like even like n heaps. If you can do the nim sum, if that nim sum is essentially, if you can bring it to 0, then basically you have solved it. So a good strategy is you take n minus 1 heap, you calculate the nim sum, and basically you take the n minus heap with the least amount of value and the heap. So for example, you have heap value for all the heaps represented as something like, let's take n, you do the max of that. Max of n basically is the heap you don't even play with. You do the nim sum for all the other heaps, so n minus 1 heaps, and then whatever that nim sum comes out to be, you just actually remove that many stuff from the max heap, and you can continue doing that and you'll win the game. Sorry. And so there is like Vaidov. Now I would not like to go there. It'll be a bit complicated. Like so, the cool part about this Vaidov name is you get a Fibonacci sequence in Vaidov name. So yeah, we are moving on to astronomy. If you guys have any questions with regards to the combinatorial game theory part, do ask me. I had plans for actually doing some other games too, but again, in because I'm actually running late and now actually.
Just a comment.
Uh,
I should admit that I've never thought of games from a mathematical or from a scientific perspective before. And if I come to think of it, that when I grew up, we used to play various indigenous games. And if I look back from how long those indigenous games actually come as far back,
uh-huh.
it makes me think in terms of if our forefathers ever thought of those games, perhaps from a mathematical perspective, even though they didn't call it that, or it was just, or they just invented them without
Mhm.
thinking the mathematical side of things.
Yeah, I think it's the second way around. Yeah, like, but I mean, who knows at this point? I mean, they might have actually also thought of like games as mathematical system. But I mean, looking at it, because in text you generally don't find these mathematical schemes. Like, it's more likely that it is the second way around. But I mean, again, nobody knows at this point.
Hmm.
Like, there are so
Okay.
many indigenous games which are actually being used as you said. I mean, I think like in India we had this game called uh, Bagchal, which actually is like which is about a wolf and four sheep. So you can actually find a combinatorial game theory generalization for that game. There's so many like different kinds of games. Like there is a game called Amazons, which is based on like a South American game which is played. So that is why the name Amazons. And like I think there's also a Hawaiian game. I don't remember the name of it, but that is also very common. Like you find in a lot of combinatorial game theory textbooks that these games are like used, and they're not like very difficult to understand anything. They use very simple principles. So like, and yeah, you find this cool mathematics around them. It's actually like, very elegant and surprising.
Okay. Thank you.
Uh,
Any more
yes.
questions or comments on the previous presentation, colleagues, before he wraps up with the last part? Okay, there isn't any questions. You can move on.
So I think because we have limited time here, uh, I can actually quickly go through, but I think theoretical part would not be the best at this point. So I want to actually show some presentations where I go to like what I was doing. So you guys might know of Stellarium. It's like a software. It's a very cool software. So what this software can do is you can literally go to any star, for example. I can actually zoom in here. So at this point, I have a field of view of 120 degrees. So this is basically set to Johannesburg. I set it perfectly for like there. I mean, this is probably the sky for 14th of but tomorrow, literally 12 p.m. around this time, like perfectly mimics the sky. Like just that I have removed the atmosphere to accept that because of atmosphere and pollution, you don't see the sky like this. But if you do not have atmosphere or anything, this is how the sky will look like. If you see all these stars, galaxies, so that you can see this. This is essentially Milky Way. Like you can see the long Orion belt here as well. And yeah, so I want to actually tell everybody about this. So this can be used in a lot of different ways. Like when I was little, I was not told about all these tools available, but now at this point, you have so many tools available. And when I look at them, I get surprised. I like get to learn about a lot of cool new things every single day. So basically, you can change the location in terms. So for example, this thing, as you can see, this can change the location, change it to any kind of longitude, latitude. You can change the elevation too. So like, if you want to, for example, if you want to maybe say something like, but very like, let's say very high up. Yeah, so you can do that too. And then you can put the city of wherever you want to actually view. And yeah, and, uh, close the window, and now it's set to like this. And then I like again field of view. I have set it as 120, but you can change that too. And then I also have the time, so I can actually go. For example, let's take you see that basically because the Earth is revolving around the sun, the sky, like the stars that you see now, you won't see the same stars in like 6 months. So you'll see a completely new set of constellation as well as stars. If you want to see constellation, they have a very cool constellation map, so you can see these. cool figures. So, like for example, if you click on those things, you actually know which constellation this star. For example, this is Hadar. Hadar belongs to uh, yeah, Centauri. So it has 88 constellations. So all the 88 or 98, something like that. All the major recognizable constellations that are available. So yeah. Mm, I can actually switch it off as well. I can also create those all the constellation labels at this point. You can see like now it has like this. Now if I add both of them, so now you see. I mean, this is like an eagle. You actually get to see like how this happens. And I was talking about time earlier. So yeah, for example, let's change the time. Let's see. You see these constellations moving, right? So you see they're moving southward the because the Earth is revolving around the sun. Now, also you have if, for example, South Africa lies in wait. Let me actually. It is minus 26 degree south and 28 degree east. I mean, longitude does not matter. Latitude is what matters. But so at this point, you have for example, at summer solstice, the Earth will be tilted towards the northern hemisphere, but now it is completely because this is winter time. This is winter solstice around that time. Winter solstice is like 22nd of December. So at this point, you'll be having this. So you'll be having a completely new set of constellations on the sky. So pretty, you can mimic that too here. And then it works in area and declinations, which are like you can think of them as latitude and longitudes for the celestial sphere. So every single star or celestial object has a area and declination, mm, which basically refers to its position in the celestial sphere. So every like the whole of this is like a celestial sphere. And yeah, so I was going deeper into this. So they have multiple surveys too. So like they have Slow and Digital Sky survey, they have Sigmart survey. There's so sorry, Simmart survey, like a lot of surveys. I generally use it on generic settings, but if you want to actually explore it, you can go there too. Uh, so yeah, I think I'll remove the constraint. So for example, if you were to go into like, for example, if you want to zoom in on a star, you have all these properties. And if you want to see how it moves, you can actually also. So now you see sun coming out. And yeah, you can go even quicker. You can go seriously. You can go to speeds like you see, like we are going way in the future. Oh yeah. I think it works up to a certain point. So yeah, let's stop here. So this is like the date that is set right now is 12th of August 2030. So 5 years in the future, you can see the sky. I mean, because the celestial movements are very like it can be easily tracked. You can actually do these kind of things. These are like these work on very simple yet elegant physical principles. for now, I mean, we are so for example, if you want to actually zoom in on a planet, all you got to do is, I mean, this is like one way of looking at. So, for example, I can change. Oh wait, this is moon, I guess. My bad. Yeah. So yeah. So this is like different ways of looking at moon. You can like literally look at how different telescopes. So, for example, I can change the telescope to. Oh, yeah. Yeah. This is like mid. So there is some similar telescopes. So I can also change the ocular, which is a bit like a lens. So its functionality is a bit similar to a lens. Or it's also like how you want to view it as well. So, for example, this has a focal length of 6.3 millimeter. Uh, and you can look at a different lens. I mean, you can see it, look at multiplicity. Simply, I mean, if you want to simply understand multiplicity, it's similar to zooming power at this point. So 1 upon the multiplicity is equal to the zoom it will produce in ways. Uh, uh, to with paired up with a given lens. I mean, you have a collection of lenses in telescopes. Most of the like the bigger telescopes have mirrors, but yeah, these like for example, Celestron has both of those. So this has Celestron luminos in this. So you can see those clear craters of the moon. I mean, I can if forward time. Let's see, a moon changes. Let's see, forward. I think it kind of crashed because I went too fast, I guess. It went. I think. Hmm. So you can do all these things. I mean, I did not actually go through everything. So the remainder of time, I'll actually go through this. So this basically creates a sphere. For example, if I select Capella, which is a star, you can basically all these things are very important too because you also get to know about the absolute magnitude. So this also creates curiosity. What exactly are these? So absolute magnitude, for example, is that like the real brightness of the star, not to factor in like how close it is to the sun, sorry, how close it is to the earth, while there is also a concept of apparent magnitude, which actually factors in how close it is to the earth and like how bright it looks for an observer on earth. So there is like there is a physical formula through which you can convert absolute and apparent magnitude based on distance and like the value of absolute magnitude. See the so you have like azimuthal angle. So azimuthal is like a, a bit similar to a, RA and declination. RA is basically right ascension. Azimuthal is basically something that goes directly up. So azimuthal can be imagined as being with a certain angle with respect to declination, and that particular value of azimuth. So you can actually that is basically given in steradian, which is the value, which is the unit to calculate uh, 3D angles or solid angles. And well, I mean, I think I did not cover a lot of this, but yeah, wait, I'll actually cover them with the time I have. So yeah, I mean, this actually changes it to a telescope perspective. So for example, if you have a telescope space placed here, so you can actually, for example, if you're setting it up, you can perfectly see how it will look through a telescope's perspective. And then you have um, then you can add all these deep sky objects, like all the clusters, for example. I can go deeper into cluster. Right? The cluster is like a building ground, or like the birthplace of stars. You find a lot of stars in a cluster. So there are two types of clusters of free clusters which don't have that much star density, and then there are globular clusters. This looks like a globular cluster because you see a lot of stars in a very tiny amount of space. Though it's a bit different than nebula. Nebula is like a proper birthplace because clusters don't have that much gas and dust such that they can cause star formation in ways. The Sirius is like one of the brightest objects on the night sky. So yeah, it's also so like, for example, if you want to see Sirius, like you can again change the telescope and you can like do a lot of things. You can go here, you can change the sensor to like, change the pixel settings, like change the resolution and then rotate it if you want. If you want to actually do some kind of spectroscopic things, you can also add a prism in between. I mean, these are too much stuff. I mean, personally, I would not recommend doing all these things, but yeah, there are a lot of these things you can do. So yeah, this is on that. This is like a daytime dawn spent. And then this basically this is realistic. So I told you now I actually had removed atmosphere. So this is what it would look like. If you actually look at the night sky. And then you can also look for comet showers. I mean, you can do a search of stuff. So, for example, I have done a lot of search for a lot of different things. So you can see this and all the searches of meteor showers. You can like basically download this data and then go into this and actually see those comet meteor showers, and then those are pretty good spectacles. All you got to do is download this and first export this and then like set the conditions and you're good to go. And then well, this is like the night like red filter. You can add grid lines if you want. Let's go. I think to a night sky. Yeah. So you can also add planet labels, for example, now, and labels for a lot of things. This were like labels for deep sky objects. So yeah, we can zoom into Venus to change stuff, change the lens, and yeah, this is very magnified image of Venus, so you can see like some part of it. Let me actually try to zoom in. This is like the lens. Yeah, I think it will look. Yeah, Celeste luminous. So wait, I think I am remaining with one or two more stuff, and then yeah, good to go. You can find out. You can do searches using this. You can literally search for objects, and then you can put positions. These are for like people who are really interested. You can put the coordinates and actually get to know about stuff in RA and declination. Obviously, as I told you, those are like the language. If you want to go deeper into, like if you want to do a survey or if you want to look out for objects, you place those values in RA and declination. Those are like the coordinate system if you want to look out for a star or a galaxy or some or a stellar or a celestial object. Mm, you can basically also do a search for solar eclipses. These are for total solar eclipses. And then you can export maps and then you even calculate solar. You can also calculate solar eclipses for other planets if you want. And then these are like these are again galaxies. All of them. Then you can also do a deep search for all these objects. This, yeah, I mean, I can select multiple. I can go to any object at this point. You can go to dwarf planets too. I think I like to do a search. How dwarf planets. Like, yeah. Uh, for example, this is the comet. It, but I think I would not like to actually extend it at this point. I mean, it's already late. I mean, you can check it out. I mean, there is one more platform called Universe Sandbox, which actually you in which you can actually do simulations. Like you can place, for example, you can replace a sun with a star which has the mass of 5 solar masses, even like hundreds of solar masses as well. You can put a black hole at the center of the solar system. You can see how that would affect the planets. You can realistically see how temperature goes, or you can even actually throw projectiles towards Earth. You can a cool thing that you can do. They also have tutorials for like some realistic phenomena. For example, how Saturn uh, got its ring. So like you can actually see like a satellite of Saturn, which is very close to it, and then actually because it was really close to it, uh, it kind of was in its orbit, and like it was not gravitationally bound in ways. So it basically the gravitational forces were way too higher than the centripetal forces that you had. So at the end, it crashed down, and yeah, you can see the ring formation in real time. You can see all those things in Universe Sandbox. And well, yeah, I would like to also show one more thing, and then I conclude it. There is this something called Zooniverse, which is basically a citizen science program. So where like even educators, and you can also tell people who are in high school, all they got to do is they'll be shown pictures and they have to identify objects, like count them. Like for example, there are some surveys which actually tell you to count the number of animals in a given picture, and yeah, like locate them, mark them. There are also some surveys about the stars, some celestial objects, some asteroids in a given asteroid belt. Those information are like used by researchers then to actually like, model stuff. So they have like a, a lot of projects. So like, they have medicine projects. Personally, I have done this for Astro only, and that was really fun. So yeah, uh, yeah, sunspot detectors. So, and then there is also a NASA Citizen Science program that you can also look out for. I can share my meeting presentation if you guys want. I'll actually also add all the links that I actually talked about, which you can look out for yourself. I did not get to play some more games. I had like a website which has like a series of 50 combinatorial games. Uh, Thank you, everybody. If you guys, if anybody of you have any questions, please, I would be very happy to answer all of them.
Thank you, Parth, for sharing the two presentations. And thank you for sharing the applications that could be useful to us as educators. Which can anybody name any one application that they had about from this presentation that they are probably going to explore? Anyone? Okay, looks like we're a bit shy today, but thank you for sharing things like Stellarium, I think you said.
Yeah, Stellaria.
Yeah, it looks like quite a fascinating application for one to use to view the local skies and all that. Thank you so much. That being said, any questions, colleagues, or any comments for the speaker?